Hello. Hello. Good morning and good evening, and or could be a good day, and to people around the globe. And welcome to the Data Analytics Colloquium. My name is Carl Ho. I'm the co-host of the Colloquium, and let me introduce my other co-host, Professor Peter Pan, and also we want to express a really appreciation for a very special guest, Professor Vito, and he is going to be our special guest speaker today. And allow me to introduce Professor D'Orazio, and he's Associate Professor of International Relations, Political Science at the University of Texas at Dallas. He's currently his research interest is at the intersection of conflict studies and computational methods. And today he's going to give a talk particularly pertinent to data science students and practitioners because he's talking about automated machine learning. The title of his speech is on forecasting conflict using automated machine learning methods. And Dr. D'Orazio has published over 20 articles and in journals in the U.S. and also he has his research is supported by National Science Foundation grants and the Defense Advanced Research Project Agency, DARPA. And now today he's going to present a paper which is an award-winning paper in this research. They want the violence early voting system competition, and particularly in the area of Africa. And now let me pass the time to Dr. Pan. Would you like to introduce our colloquium too?
Yeah, thank you, Dr. Ho, and Dr. Ho D'Orazio, and everyone online, and good morning and good evening. Let me just give you a short introduction to DAC. We coined this as a data analytic colloquium. This colloquium is about to introduce the latest in data science, focusing on applications in social, political, and policy sciences. And this is second year, actually, well, second season, if you like. So we try to invite well-known scholars around the globe. For the previous years, we have quite a successful series. So if you may, you can go online and check. We have those on tape videos recorded, and that's very interesting. So for the previous season, we kind of focus on the election, so because it's a hot issue. For this year, and we have a more diverse and topics, including today's topics is about the conflict. So personally, I'm excited to have Vito here in this series. And I want to personally thank Carl for coordinating all the things to make it happen today. Thank you.
All right, I think without further ado, I think we will let Professor D'Orazio take the podium virtually. Thank you.
All right, great. Thanks, Carl. Thanks, Peter. Hi, everyone. Let me share my slides here and just make sure this is working okay.
Yes.
Okay, great. All right, so I'm going to have this on full screen. And so I won't be able to see any questions in the chat. So if someone does ask a question in the chat and someone sees it, you could just jump in and interrupt me to let me know that you have a question. I encourage you to ask questions along the way if you have any questions to ask. You know, this can be as interactive as you'd like it to be. So today I'm going to talk about predictive modeling and conflict forecasting. I'm going to start off the talk motivating conflict forecasting a little bit with some more policy applications. And I'm going to give some kind of general introduction to predictive modeling and data partitioning and cross-validation, which is very helpful to understand. It's like the background for conflict forecasting. And then I'll get into the conflict forecasting model with and paper that Carl mentioned earlier, and the use of automated machine learning for conflict forecasting. Okay. Okay. So predictive modeling is kind of everywhere nowadays. But conflict forecasting is also becoming very common. So here we see some excerpts from the US State Department, in particular the Global Fragility Act in 2019 and the Global Fragility Strategy in 2020. And the idea of the Global Fragility Act is to strengthen fragile states where state weakness or failure would magnify threats to the American homeland. And of course, part of that is identifying where those threats might be, right? And so you're going to create some expectations about where you think threats would come from, and then sort of invest in stability in those places. And the Global Fragility Act and the Global Fragility Strategy that kind of implements that the policies are pretty explicit about forecasting and understanding risks of fragility and expectations of violence, and incorporating that into the decision process. That's just one example from U.S. government. Here's another example from the United Nations, and it's not really specific to forecasting violence, but it's more forecasting things related to humanitarian affairs. And so there's a question, for example, like when can the UN trigger the release of funds from the Central Emergency Response Fund? And so they create these things called anticipatory action frameworks. Right? And the idea of these is that they're going to use predictive modeling, for example, in areas of food security, to get sort of ahead of the event, right? With the idea being that if you wait for food to run out, then you've waited too long, right? You want to be able to release those emergency response funds that the UN has at its disposal. You want to be able to release them before food runs out, right? Or you want to be able to release funds before a hospital gets overrun. And the way you do that is with predictive modeling, right? You can use data to figure out, to create realistic expectations about when the food might run out. So this is not really, this idea of creating of predictive modeling or creating outlooks isn't exactly new, but the way we're doing it nowadays is new. So this is an example from the Council on Foreign Relations, which is a think tank. And within that think tank, there's a lot of different centers. There's a Center for Preventive Action, right? And here you see an outlook for 2020. And these are places where threats could emerge from. The methodology for identifying these threats, right, or conflicts that are, quote, this is a U.S. think tank, so it's potentially harmful to U.S. interest. The methodology for identifying those places that are potentially harmful to U.S. interest is to survey experts. So you find some domain experts, people with subject matter expertise, maybe experts on a particular region or a particular conflict, or even a type of conflict. Survey a lot of them and ask them to estimate what the impact's going to be on U.S. interests for the next year. And this is one way to do it. These types of outlooks are not uncommon. They've been around for a while, but increasingly we see that we're moving away from the sort of qualitative expert opinion and using predictive modeling a lot more to produce those data-driven expectations about likelihoods of violence or likelihoods of harm to US interests. And there are some large-scale projects that are implementing this type of modeling in several different domains. Here's one, it's called CUCAST. And it's a project that it's a project from a think tank, and it's kind of between think tank and academics to forecast the risk of coups, and it forecasts the risks of coups at a monthly level for every country. Another domain, and the one that I'm going to focus on, and is exemplified in this quote here, is in conflict. And this is by Hegre et al. It's a 2019 article that introduced the Violence Early Warning Systems project, with the big idea of this project being that we're going to forecast violence at very disaggregate locations. And the project started as forecasting violence across Africa. And as you can see here, there's in these three panels, right? They're very fine-grained forecasts. On the left is this is from their paper. On the left is forecasts they made for state-based conflict. In the middle, it's for non-state conflict, and on the right, it's for one-sided violence. And the one that I'm going to focus on today is state-based conflict. And I'll define what that is in a moment. Right, but this project, the point is this project is creating forecasts for many different types of violence. And this is going to be the kind of the main example that I'm going to use and talk about, and it's the focus of the research paper that I'll present in a little while. So this Views team really held a forecasting competition in 2020, right? And the idea was, well, they had they had their forecasting models, and they wanted to hold a competition to see if, well, can people beat our forecasting models, and if so, how are people beating our forecasting models, and can we and there was a bigger picture question of, can we combine multiple forecasting models to improve our forecasts, create like an ensemble approach where we have many different models coming together to improve our forecasts. Okay, so what are we forecasting here? So we're looking at state-based conflict in Africa, and we're specifically defining it using the georeferenced event datasets definition. And so the definition is an incident where armed conflict was used by an organized actor against another actor or against civilians, resulting in at least one direct death at a specific location and a specific date. So this is event level data. Right? They have specific location and specific dates associated with the violence. And state-based here means that one of the organized actors is a government. Right? So it's state-based conflict. So the state government has to be involved with the conflict. And it could be different types. It could be government to civilian, government to government, or government to rebel group, but a government is an actor. And that's the type of violence that we're forecasting. So some details of the competition, I'll come back to this a little bit, but it's helpful to introduce now and keep in mind. So we're going to have training data from 1990 to 2015. And then we're going to have test data made available from 2016 to 2018. And then we submitted, prior to October 2020, we submitted what we might call like true a priori forecasts for conflict at that very disaggregate grid level for 6 months. And so we created 6 sets of forecasts for every grid in Africa, and also at the country level. So every country in Africa and every grid in Africa for 6 months. And these were sort of the true a priori forecasts. All right, so just to visualize that just a little bit here, right, there were 2 tracks. One was the country level track, which you see on the left here, where you're forecasting monthly level violence monthly level state-based violence for the entire country. And the other, which you see on the right here, is at the grid level. So it's very disaggregate. So this is, in each of those grids in the next month. And here, the grids are colored purple and yellow, where purple grids experience no conflict over a given time period, and yellow grids experienced some type of conflict. The model that I'll be discussing actually won the competition. It won the grid level competition, not the country level competition. It won the grid level competition for both predictive accuracy and originality. And I'll talk about that model in a little bit and what that means. And also reflect a little bit on maybe some differences of why the model does well at the grid level and didn't do quite as well. It did okay, but didn't do quite as well at the country level. Okay, before I go into sort of the background on predictive modeling and data partitioning, does anyone have any questions?
Yes, hi. This is Glenn Cooper. I have a question on the violence data.
Mm-hmm.
How confident are you in the level of reporting that violence is occurring?
Yeah, that's a great question, because we are totally beholden to the quality of the data here. And so the data for this project come from the GED data set, which is the georeferenced event data set. And that data is coded from news reports. And so it takes along with it any biases that may be associated with those news reports. And so, while I'm confident in the data, there are of course things that are missing, and maybe some incidents, that make it into the data are misrepresented. But I think on the whole, the quality of our news, especially in the last 10 years, is quite good. Is quite good and doesn't have the sort of as many Western biases as it used to have. So I think the quality of the data is good, but it's important to keep in mind.
Yeah, we have a hand here in the audience too. Tianyi, do you have a question? Please speak up.
Thank you, Dr. Ho. Well, Dr. Durazzo, as Tianyi, UTD student, I have a quick question for you, Professor.
Sure.
So when you showed us the graph that indicate the yellow dot indicate the conflict happened, right? But we're more. Are you more curious about the frequency of the incident rather than the scale of the incident? To me, I mean, well, I'm from a public administration major. To me, I feel like the size, I mean, the more severe the conflict or is more interesting or more, I would consider that as a dimension.
Yeah. So
for this case, you only considering the frequency as a main factor, right?
Two things I want to say there. So one, this is just an example here. It only represents whether or not a conflict occurred at all in that particular grid. And the idea is just to kind of show you, like just how fine-grained the grids are and give you an overall sense of where the data is reflecting conflict in Africa. Mm-hmm. The other part to that question, what we're actually going to be forecasting is the log number of fatalities in the grid. So that's actually what we're going to be forecasting. And well, my model will forecast the log number of fatalities. The views competition explicitly wanted the change in the log number of fatalities. And so I get that by forecasting 1 month in the future and then 2 months in the and then subtracting them to get the change from 1 month to the next. But you could also forecast that change directly.
I appreciate it.
All right, one more question in the audience. Professor Mei Yuan, please go ahead.
Yes, well, thank you. My question is that if we overlay the settlement data with the right figure, how well correlated those locations with human settlement?
Not great. Not great. And we have, so the views competition made they put together an incredible resource for forecasting. And I have the link in here. I'm happy to share if anyone wants. It's out there on GitHub. And they've compiled a ton of data, including population estimates and other things that show like development at the grid level, like they have like the different night lights measures. Actually, what my model shows is that stuff's not very helpful for forecasting violence. All right, if you want to forecast violence at the grid level, I'll get into this when I get to the actual model itself. The best thing you could do is use violence, because there's plenty of population centers in Africa here that are peaceful. Does that answer the question?
Yes, thank you.
Okay.
Yes.
Other questions?
Yeah, please feel free to type in a question in the chat box if you have access to that. We will read it out, or you can raise your hand or speak up. Yeah, thank you. Please proceed. Yeah.
Okay, great. Okay, so I'll try to go pretty quickly over the next 2 sections so I can get to the research paper. All right, so but here's just a little background on predictive modeling and data partitions. Okay, so we can write a model as we see here. This is very straightforward, nothing special, right? Y equals f of x plus epsilon. Y here is our dependent variable, and x are our predictors, right? F is the function that's going to relate the dependent variable to the predictors, and epsilon is an error term that's going to contain both reducible and irreducible noise. So when we're building models of any type, right, that's going to take this form, we have a lot of choices to make. So we have choices about what observations we're going to use, what observations we're going to use in our data, what variables, like what predictors we're going to put into our data, our choice of function. We're going to have to also make decisions about how we want to assess that model, and to use that assessment to maybe choose between different modeling decisions. So one of the main things that guides these choices that we're going to make is what type of model we wish to build. Predictive models are those where the researcher values predictive performance in selection and assessment. Right, that's what distinguishes them from other types of models. Predictive models are those where the researcher values predictive performance in both selection and assessment. This is different from what we might call inferential models. And with an inferential model, the researcher is really trying to operationalize a theory. They're trying to create a model that operationalizes some theory. And while they might be interested in the predictive performance of that model, it's not necessarily predictive performance that drives your selection. What your choice of f is, for example, and what variables go in the model, right? It's not necessarily predictive performance that drives that. Rather, what drives that is the accurate operationalization of a theory. And predictive models are also different from experimental designs, where the focus, right, a lot of those decisions that you make is so that you can accurately estimate a causal effect. Like you care a lot about, getting the beta hat right. With predictive modeling, we care about getting your y hat right. Right? We care about getting our predicted values as close to y as possible. And often to do that, now this isn't to say we throw out domain knowledge, right? And it's not to say we don't use expertise, because domain knowledge, so in my case, it's knowledge about conflict processes, knowledge about conflict data, coupled with knowledge about predictive modeling. Right? It is really the way to build the best type of predictive model. You're not throwing out domain knowledge, but when you're selecting and assessing the model, you do it with respect to improvements in predictive performance. And we assess these models using performance measures. So there's many different types of performance measures, and it depends on what task you're doing. So for conflict forecasting, we're going to actually just be using the standard mean squared error. Other performance measures were part of the views competition. Other more complicated, like proper scoring metrics, were part of the views competition. But at the end of the day, mean squared error was also included, and that was really the main performance measure that was used. But it's these performance measures, once we decide on a performance measure, that allows us to compare different solutions, right? So it's a key part. So this idea that we have these performance measures, and we use those performance measures to select our models is, again, something that sets predictive modeling apart from inferential and causal modeling. Right? In those inferential and causal modeling, we don't use performance measures to select the model. But in predictive modeling, we do. So for example, if I'm using mean squared error, this is just a simple formula for mean squared error. I might hold my variables and my data constant, but I might want to look at two different learning algorithms. So for example, OLS and random forest. And then I could compare between the two. Okay, which has the lower mean squared error? If mean squared error lower is better. And then that's an example of selection, right? And so I'd select the lower of the two, which in this case is OLS. Okay, so that's one general part of the background, right? That's very general predictive modeling. Second thing to keep in mind is data partitioning and cross-validation. If we use all our data to fit our models, it's going to cause a problem. And that problem is called overfitting. Right? And this is the idea that our model is not going to generalize well to new data, to out-of-sample data. Right? We have to train our model on some data, and if it's fit too closely to that data that we train on, it's not going to generalize too well to out-of-sample data. And so, for example, if we want to build a conflict forecasting model and put it in production, right? And when I say put it in production, I mean, well, we're gonna train it, and then we're gonna actually use this model to forecast violence for the next 6 months. And we're not just going to use it one time, but we're going to every month, right? We're going to take our new input, our new month worth of data as input to the model, and get a new set of predictions. Right? And so we're going to keep doing that month after month after month. And so we have a model that's in production. You don't want that model or any model to be fit the training data too closely, because then it's not going to do a good job predicting or forecasting that new out-of-sample data. And this is particularly a concern as our machine learning algorithms become a lot more flexible and have a lot more tuning parameters that can fit the training data very closely. So we try to account for overfitting with data partitioning and cross-validation. And there's a lot of ways to do this. So so data partitioning on the whole allows us to assess how well our model will generalize to new cases, and cross-validation mitigates our concerns that a model is overfit and won't generalize to new data. Right, and so here's a visualization of what goes on when we partition data. Okay, we split it into first our training data and our testing data. Right? And our training data is where our model selection takes place. All right, so this is the data that our model is actually going to see. We're actually going to tune the parameters of the model using the training data. Right? And then we're gonna compare different choices. For example, we might compare different sets of variables or different learning algorithms. Or, as we'll see, different automated machine learning systems. All that's going to be done with the training data. And then we're going to assess on the testing data, with the idea being that once the selection's complete, we then use that model that we've selected to create predictions or forecasts on the testing data. And that's going to give us some accurate performance measure for how this model will do in new out of sample testing, right? Because it's never actually seen the testing data. Now, when we partition data into training data and testing data, there's different things we might take into account, and we often have to think about what the structure of our data is when we decide, well, what goes in the training data and what's going to be in the testing data. Okay, so if we could think of just like a simple case where our data are independent and identically distributed. Okay, then in that case, with data are IID, we might just randomly partition it into training and test sets. All right, so for example, 1,000 observations, right? I might randomly sample 70%, put it in the training data, and then keep the other 30% for testing. And it's a real random sample of those 1,000 observations because the data is IID. And so where independent means that an observation of some event is not influenced by other occurrences or non-occurrences of that event. And identically distributed means that the events are generated by some same underlying distribution. And so let's just say we were able to, we have confidence that we can just randomly sample in that way. So we could do that, put the 70% in the training, and then keep the other 30% for testing. We can then, using our training data, we would then do cross-validation. Again, this is a way to select a model. Right? So notice we're not using the testing data here. Right? We're still using the training data. And there are lots of different variants of cross-validation, but the basic process is that we are then going to take the training data and actually sample the training data, fit the model using the data that we sampled, right, which is a subset of our training data, and then assess the model's out-of-sample performance using the training data that's not in the sample. And we'll call that data that's not in the sample for that particular instance, we'll call that validation data. So there's like the training, validation, and testing. Again, all of this is to get some reliable estimate of how the model is going to perform out of sample and to mitigate the effects of overfitting. So this procedure may be repeated any number of times with different types of sampling. And as I mentioned, there's many variants of cross-validation and many different types of and also different ways to go about data partitioning. Right. So I said that when we partition the data, it's important to keep in mind the structure of the data. And so in conflict forecasting, we usually do this a little bit differently. We often set up our data partitions, and this isn't always the case. People do this differently, but we often set up our data partitions to appear sort of like as if the model were going to be put in production. And so we would set it up as the views forecasting competition set it up, which is, here's your training data from, for example, 1990 to 2015, and now all of the testing data takes place after that point in time. So it's as if you had if you were in 2015 and you now wanted to build a model that you were going to put in production for the next 3 years, say. Right. So you have, you're in 2015, you have all that data from 1990 to 2015. Well, train it however you want, and then assess how its performance would have looked over that 3-year period, assuming you don't retrain it, which is a different approach that would lead to some different partitions. Right, but we're going to assume we're not retraining. So that's just another way to do the partitioning that takes into account the structure of the data and really what you hope to do with the model as well. Okay, any questions on that? I know that was kind of quick course overview of predictive modeling and data partitioning, but any questions on that?
Go ahead, May. Go ahead,
Yes.
please.
Yes, thank you. Can you give us an example of what are your x's and what is your y?
In the views competition?
No, in your model.
For the conflict forecasting model?
Yes, you very high level explain the fx equal to y. So what are the x's and what is the y? Is the y just occurrences, yes or no, or is frequency of the violence?
Yes. Thanks. So I'm going to get to that in a minute. So I'm going to punt on it for right now because I have a slide where I'm going to discuss the particulars in just a minute. Okay,
thank you.
Yeah.
Tianyi, do you want to have a question?
Thank you, Dr. Ho. Professor Durazo. I'm trying to figure out if I am following you. So what you're doing here, the training data and the test data, it reminds me about the discriminant analysis, which we have an analyzed sample and the holdout sample. We're using the analyzed sample, well, you call it training sample, to generate a dynamic system of a measurement or a model. And we have some holdout sample, which you call this test sample here, and to actually test the validity of this dynamic sample, dynamic model, right? That's what we're doing, right?
That's exactly it. Yep.
And I have some, thank you, I appreciate it. And I have similar question as Professor Yuan, and I'm not sure I understand the outcome. Say for example, for the discriminant analysis, you have a kind of a dichotomy outcome, either 0 or 1. That's the discriminant analysis. But for this one, I don't understand the DV. I don't understand the output that we're looking for.
Yeah.
Thank you. Appreciate it.
Yep. Thanks for the question. So I'm going to get to that now in this next set of slides. This set of slides was more high level, kind of what is predictive modeling and what is data partitioning and cross-validation. I'm going to get to the specifics of the actual forecasting model now. So let me go ahead and do that. Okay, so this is our conflict forecasting model. All right, this is the idea here. All right, so we have y at time t, which is state-based violence, and specifically it's the log number of fatalities. And it's the log number of fatalities in a grid at time t. And we have both x, so we have different predictors, right, and legs of those predictors. Okay, so we are using information from earlier periods to forecast violence at time t. Right, and that's the main restriction here. So it doesn't actually matter what's on the right-hand side here. Right? It can be whatever you want, whatever you think is going to be useful. But the main restriction in this competition and in this type of modeling is that you can't use information at time t or later. Right? Otherwise, it's all fair game. So you can have y, a leg of y that can be a predictor. And indeed, of course, that's going to be a pretty good predictor. Okay, so I'm going to integrate this now a little bit with automated machine learning, right? And so we have our forecasting model, and we estimate a bunch of different solutions. Right, so y hat is our forecasted conflict at time t. Again, our x's and y's are exogenous and endogenous features at time t minus k, where k is some value, 1 or greater. A is some learning algorithm, and we're not right now, we're just leaving that general. So some learning algorithm could be like OLS or random forest or stacked ensemble, which I'm going to introduce in a moment. And that whole thing is a model that's parameterized by theta, right? So that's all the tuning parameters that go into it. And we're going to estimate a bunch of these different solutions, like a lot of these different solutions. And the goal is going to be to minimize the loss, where again, we're going to focus just on mean squared error, keep it simple. The competition did have some other metrics, but mean squared error is the primary one. So we want to build a model. That's sort of the problem. Now, what goes into it? All right, so there's a few things that are going to go into it that a lot of it stems from a paper I wrote in 2020 as kind of a analysis of many different conflict forecasting models. Right, but we want to put into it that domain expertise, that things that we know about both conflict forecasting and predictive modeling. So I came up with 3 things that are very important. Right, one is that the model has to be very flexible to capture nonlinear relationships. When you read through the literature, there are tons of nonlinear relationships in conflict data. And this quote from one of the earliest papers that uses neural networks to forecast conflict really drives home the point that there are expectations that the things that predict conflict are highly nonlinear and massively interactive and heavily context dependent. So we need a lot of flexibility to capture nonlinear relationships. We also want to emphasize the endogenous nature of violence. And so what I mean is that violence very often drives more violence. So it's not even just that violence, yesterday is a good predictor of violence today, right? But it's also like the number of violent events that took place yesterday, not just the overall level, but the number of violent events that took place yesterday. And it's not just yesterday, right? It's last month and the month before that and the month before that. And it's also not just what happened here yesterday, but what happened in my neighborhood yesterday. So what happened in the grid next to me, right? So there's a lot of temporal and spatial dependencies associated with violence. As this quote here from another well-known paper, but more recent, says, right, the modeling literature has demonstrated a leading predictor of future violence is simply the prior distribution of violence. And in fact, I take it even one step further and say that we can do a really good job predicting violence using only the prior distribution of violence. It's not only a leading predictor, it's in some sense, in a lot of ways, it's all you need, but you have to do it right. And the third, which I spent a lot of time earlier talking about, is to avoid overfitting. Right? And overfitting is going to be especially problematic when we start working with very flexible learning algorithms, as we are, and very highly disaggregate data, where a lot of things don't move much over time. And the target variable itself is very imbalanced. Right. So overfitting is a big concern here. Okay, so what are some things that we're going to do? So we're going to on the flexibility side, we're going to bring in automated machine learning, and we're going to test 3 different automated machine learning systems. They're all open source and publicly available. H2O is a private, I guess,
commercial.
I'm sorry?
Is this still commercial? I think there's a free account, right?
Yeah, it's commercial, but you can get free access to it.
Mm-hmm, mm-hmm.
Yeah, it's a commercial.
Yeah.
It's a commercial product, but you can get free access to it. Exactly.
Cloud-based, yeah.
Yep, cloud-based.
Mm-hmm.
And then there's 2 other AutoML systems that were developed as part of DARPA's Data-Driven Discovery of Models program. One we're just going to call CMU because it was developed at CMU, and at the time they didn't have a name for it, although I think they've named it since. And Alpha D3M, which was developed at NYU. And they're all automated machine learning systems. I'll explain what those are in a moment. And then we're going to experiment with different variable sets. But particularly, I'm going to focus on variable sets that limit exogenous predictors, right? So that limit things like measures of development, measures of population, measures of geographic terrain. So we're going to limit those things and focus on creating many different measures of conflict itself. So again, this will include like a measure of conflict last month, a measure of conflict 6 months ago, right? Not just the severity of violence, but also maybe the count of violent events, spatial variables, things like that. And then going to do some kind of somewhat standard cross-validation procedure to avoid overfitting. So the idea, so AutoML might be new to some of us here, and the idea here I think is illustrated by this figure. Okay, so imagine we have our grid of different solutions, and each of those solutions is represented by a box here, right? Each box here, each cell is a solution. And by solution, I mean there's a combination of, let's just say, learning algorithm and choice of variables, right? So let's keep it simple, right? You have your choice of variables that your predictors that you're gonna put in your model, and you have your choice of learning algorithm. We can call that a solution. Right, with very limited search, so if we look at the left panel, right, with very limited search, what we might do in the absence of something like automated machine learning, right, we might select all that stuff in advance. We might say, okay, I think these 2 or 3 learning algorithms are good, and I think these 2 or 3 variable sets are what I want to search. And you search a limited number of solutions, and then you compare among them. Now, you're careful to avoid what are just nonsensical solutions. Those are the 6 cells that are highlighted in black here, right, to just conceptualize it. We always have maybe those are like, variables that are in the data but don't really belong in the model, or maybe they're learning algorithms, or that just don't make sense for this particular type of problem or something like that. Or maybe they're variables that you could be in the model, but you don't want them for some particular policy reason. So, but you're very careful to avoid those things. The idea of automated machine learning is that we're going to expand to search over many, many, many more solutions. Right? Many more algorithms, possibly different combinations of variables, and possibly as automated machine learning algorithms become more developed, they'll do lots of other things as well. When you do that, though, you're bound to get solutions that are nonsense and that you don't want. So what this means is you can't just pick, the best performing one and accept it blindly. You have to then go in and kind of inspect the model that the solution that the AutoML engine found to check if it does indeed make sense. But the idea is that you're opening up this space, you're searching over many more solutions. And remember, this is predictive modeling, right? So what you care about is predictive performance. And if you're able to search over many more solutions, you should be able to improve your predictive performance. You should be able to. Not necessarily going to be the case, but you should be able to. So just to mention a few things here. So AutoML systems, one thing that they all do is they all search over different learning algorithms and different parameterizations of each solution. All right, and so this is kind of if it's going to be called an automated machine learning algorithm, it's almost definitely going to do this. So it'll check over different neural networks, SVM, random forest, and other machine learning algorithms, and it'll maybe even look over, and it will also look over different parameterizations of each of those, and you'll be able to compare them. There's lots of other things that we do, though, with our data, and when we actually, build a model that could be accounted for by AutoML systems. So think, for example, missing data, right? What do you do with missing data? Some algorithms handle it better than others, right? Sometimes you might want to impute missing values, or interpolate, or use listwise deletion, or whatever. AutoML systems, as they develop, could do more of this other stuff as well. They could do different things with outliers, could do different things with reducing the dimensionality of the data, handling class imbalance. There's a There's a good paper by Kennedy that looks at different ways to handle class imbalance, and actually shows that there's a lot of different methods for handling class imbalance. So class imbalance is the idea when you have maybe if you have like a rare event, something like conflict, and it's only like, I don't know, 2% of your data actually shows conflict, right? Well, in that case, you have a very imbalanced dependent variable, right? Most of the time, there's nothing, right? But and there's different ways to handle class imbalance, and what that paper by Kennedy shows is that some of them work well sometimes, and some others work well at other times, and there isn't really a very good way to know ahead of time which is the best method. And in that case, you might want to check over a bunch of them. And then there's also things that it can do with the data, your predictors itself. So maybe various types of basis functions, right? So including like squares or logs of variables. So the 3 AutoML systems used here, and this was done, I guess over a year ago now, because the forecasts were submitted for October 2020 through March 2021. Yeah, so it was just over a year ago now. So the newer there are newer versions of all of these out there. But the 3 that are used here again are H2O, CMU, and Alpha D3M, and they're all open source, and they're all publicly available. Okay, so with those 3 AutoML systems, we're going to look at 4 different data configurations. Here I call them the views configuration, which uses all the variables that are in the views model. As you can see, for the country month, that's 797 variables, and for the grid month, that's 41 variables. And then there's a top 30 configuration, which uses the 30 or so most important variables from the views set as deemed important by the views team. So they ran some algorithm and said, hey, these are our top 30. The other 2 are 2 kind of new ones that take into account those features of conflict that we want to account for. They take that into account more centrally. So I'm going to call it the DV only model and a hurdle model. It's not really a hurdle model. It's kind of like a hurdle model. All right. So the DV only features is going to include only things that can be constructed from the event level conflict data, right? Plus the structure of the data itself. So this is going to be things like the total fatalities. So again, this is the total fatalities at T minus K, right? And we're using that to forecast log violence at time T. So total fatalities, the count of fatal events, dummy variables to indicate fatal events. So maybe you want to have a dummy variable for, were there 10 or more fatalities? Were there 100 or more fatalities? Were there 500 or more fatalities? And that can help get at maybe like some types of threshold effects. And different types of temporal and spatial lags of these things as well. So the core idea, though, is that these are features that are constructed from the event level conflict data itself. Nothing exogenous to conflict. And then we're also going to use the month indicators for what month of the year it is, because in some places there's like a fighting season. You may have heard this in the news with respect to Afghanistan. There's like a fighting season. And we're also going to include country dummy variables. And then the hurdle model uses the same exact features as the DV only model, right? So again, they're constructed from the event level conflict data itself, but we're going to exclude grids in Africa that never experienced any conflict. So it's a way to address the imbalance. We're going to say, because a lot of Africa is the Sahara Desert, and there's not a lot of people there, and there's not a lot of conflict there, right? And so the idea is, well, we're going to exclude those grids where there's just never any conflict, and we'll just predict that the number of fatalities for those grids is 0, because we do have to create a prediction for the competition for every grid, you know, for the time period. And so we're just going to predict 0. And our unit of prediction, CM is the country month and PGM is the PRIO grid month. So we have our comparisons here. We have 3 AutoML systems and 4 different data configurations. And for we're going to train 6 different models for each of these. So we had to do 1, 2, 3, 4, 5, and 6 month out forecasting, right? So if it's what month is it? November, right? Forecasting conflict for December will be 1 month out. Forecasting conflict for May will be 6 months out. Here's the training, validation, and test splits again, so you can see them. So all data from 1990 to 2015 were training data, and then 1 round of the competition, or 1 task of the competition, looked at forecasts for 2016 through 2018. And another aspect of the competition looked at true forecasts for October to March that were submitted in September. Okay, so this is the mean squared error for all the different experiments that were run here. Okay, so we see there are 3 groups of models. So there's the alpha D3M group, the CMU group, and the H2O group. And then for each, right, we have the 4 different data configurations. This benchmark here is the views benchmark model. And that's different from the views variable set alone, right? The views variable set uses the AutoML engine, but it uses the views features. The benchmark model uses both the views features and the views learning algorithm. So looking here on the left, we can see the results from the PGM setting, the PRIO grid model, and on the right is the country month. So this is the PRIO grid month, and on the right is the country month. And I'm not going to go through, I'm not going to make you look at these numbers too much longer, right? But the H2O with the DV only is the one that performs best. And we could see this is the if we compare, you can compare the DV only, the H2O to the CMU and the alpha D3M, and you can compare it across different time periods, and it outperforms them in each time period for the PRIO grid month. It also outperforms all the other data configurations. The DV only outperforms all the other data configurations at the PRIO grid month. So it's really pretty solidly the best selection here at the PRIO grid month. It's not quite as clear at the country month. There's some other, it's still the best overall, but it's not consistently the best. Right? So just to look at this a little differently, right? Here we can compare the 4 systems to see which system performs best. So holding the variable set constant, we're looking at the views variable set. And on the y-axis, we have the mean squared error. And again, lower mean squared error is better. And on the x-axis, we have our 1 to 6 month out forecast. And we see that the H2O system is just considerably better than the NYU and CMU systems. We could also look within and between systems, right? So now each of these panels is a different AutoML engine. H2O is in the middle. On the x-axis, again, we have our 1 to 6 month out forecasts, and on the y-axis, we have our mean squared error. And each line in each of the panels corresponds to one of those different data configurations. If you look at H2O, you can see that the DV only is really it outperforms all the others, right? It really summarizes or visualizes what I said earlier, looking at that kind of horrific looking table. This is just at the Prio grid month level. That's what I'm focusing on here. The DV only does very well for CMU and NYU as well, but not quite. It's not consistently the best. The hurdle model also does well here for CMU and NYU. Again, the hurdle model is the same variables, right? Those variables that are all constructed from the event level conflict data, but it has dropped all of the cells, all the grid cells where no conflict is present. Here's the country month, right? Same thing. See H2O performs a little bit better. And then looking within and between systems at country month, we see the same thing, only not quite as strong of evidence for the H2O DV only combination. Still, overall, I think the best and the one that I went with for submitting to the competition. Okay, so main findings there. AutoML improves predictive performance. It does a very good job in general. All three AutoML algorithms improves over the benchmark, and the H2O solver performs best. And I haven't talked about what algorithm performed best yet within H2O, like which one it landed on. Because remember, that solution space is pretty big. It searches over a lot of different learning algorithms. The one that performed best, though, is an algorithm called a stacked ensemble. The other main finding is that the DV only model performs best, and it's particularly true at the subnational level forecasts. This finding, I think, is more important and more interesting. Maybe not more important, but more interesting. I think the AutoML finding is important because we don't really use AutoML in political science. We've actually we go through like phases with learning algorithms that we become kind of enamored with. And as a discipline, we kind of see them, one person uses random forest, then all of a sudden everybody uses random forest. AutoML breaks that kind of path dependence, which makes it important, but it should, we really have pretty strong expectations that AutoML is going to do better than any one individual learning algorithm would do. So it's maybe not quite as interesting. But the DV only model, I think, is very interesting because when a lot of conflict forecasting models are put together, the variable selection process is very intentionally driven by theory and driven by like our expectations about different types of exogenous factors. But the model really suggests that we don't need a lot of that stuff, or actually we don't need any of it when we are forecasting conflict. We could do a really good job forecasting conflict just using variables that we create from the conflict data itself. And this has some other advantages too, in that you do a lot less data work actually, right? So you don't have to worry about merging in all different data sets from all different places. It can also work with any type of conflict event, right? Any type of social event that you're trying to forecast, you can use this approach with, because all you need is the data, is the event level data itself. Everything else from there is just data work in terms of aggregations and transformations, and some, you know, like spatial stuff, spatial and temporal stuff. Okay, I'm running a little bit late, and so I said I was going to go for an hour and then take a break and come back for Q&A, and I realized it's 10:12 already. So I'll wrap up kind of quick, because that was the main thrust of the paper. But with that model then selected, you know, we can explore results to take a look at what's going on here, right? And so these plots show the grid level violence that's been aggregated up, right? And so on the left we see the observed violence, and on the right we see the forecasted violence. And a couple things to point out. For example, like Libya, this country right here, has pretty high violence, and it also has a pretty high mean squared error. So we're not really doing the model's not really doing a good job in Libya. Look at Nigeria, on the other hand, though. Nigeria has pretty high observed violence, but pretty low mean squared error. Right? So the model's doing a good job of Nigeria. Good job forecasting in Nigeria. Not such a good job forecasting in Libya. So, you know, you want to explore things like that. You want when it's time to improve the model, you want to, you know, explore things like that and think about what the next steps might be. Because of the disaggregate nature of the problem, you can aggregate results up to get forecasts for regions that cut across borders. A lot of conflicts cut across borders, right? So for example, Nigeria's violence, well, not just Nigeria, but violence associated with the extremist group Boko Haram, right? That spans over Nigeria, Cameroon, and Chad, all around that region of Africa, like the Lake Chad region of Africa. So we can take all the grids in that region, aggregate them up, and get forecasted violence. You know, here in this plot here, we see observed violence over a time period, and then for the October to March, we have the forecasted levels of violence. And this tends to be the trend. Like the observed violence is pretty jumpy, right? This is, keep in mind, this is very disaggregate data. This is grid month level data. So it's very disaggregate. And even though this here is aggregated to this region, it's still kind of jumpy. But the forecasts tend to be pretty smooth. Something that can be done, like a more policy implication of this, is that if you want to assume that there was some policy intervention at a particular point in time, and you wanted to look at reductions in violence, or I should say reductions in expected violence, right? You could look at the observed violence over a period of time and also forecast out what the expected violence would have been over that period of time. Okay? And that's one way that you can get at estimating the impact of a policy intervention. Right, so if you imagine this green line, dashed line, this green dashed vertical line is like a policy intervention, right? You're then going to observe violence after that green line. But you can also create forecasted violence for after that green line, and then compare the observed and forecasted. It's one way to estimate the impact of policy intervention. We could also look at the variable importance. I dropped the labels. Each of these bar corresponds to a particular variable. They're the top 10 important variables for each of the for CM at 1 and 6 and PGM at 1 and 6 months. One thing that is interesting from the variable importance plots is that the most important predictor is actually something that we don't see in a lot of conflict forecasting models. So overall, I mean, the most important predictor can vary from, which one we're looking at, but one that's consistently in the top 2 or 3 is the count of the number of fatal events in the previous time period. And the count of the number of fatal events is a predictor that's not in a lot of our conflict forecasting models. We tend to use the severity of the event. To measure the severity of the event, we tend to use like the total number of fatalities or the log number of fatalities or something like that. But it's actually a better predictor, if you had to choose one, is actually just the count of the number of fatal events. But it's predictive modeling, so we don't have to include one, so we put them both in there, and that improves performance. So as I mentioned, this model was entered into the conflict forecasting competition. Right, so the way it worked is there was some number, I don't know how many, number of proposals to the forecasting competition, and then of that, some were accepted, and then these are the ones that were accepted and actually, submitted results that could be tested. All right, so here we have 8 different sets of results, and each of the way to read these plots. So I'm here. Yu Lin is a PhD student in computer science, and he worked with me on this paper.
So you defeated Patrick.
I wasn't going to necessarily point that out, but because I was also an author on that paper too. But yeah, we did defeat Patrick. Yeah. So each of these is a performance measure. Each of these points is a performance measure, and if that model performed best for that given point, right, it goes out to the edge, and then everything else is normalized compared to that. Right, and so you can see that. So basically, the more colored space, the better. So we did really well overall at the PRIO grid month level. Now, we also submitted at the country month level, and we did okay. Right, we're kind of like middle of the pack at the country month level. So just to wrap up some conclusions from this, right? So the method of combining automated machine learning with this DV only approach has a lot of benefits. It works very well at disaggregate levels. It requires no assumptions about learning algorithms or exogenous factors. It requires very little external data and can be used with a lot of different any type of socio-political events. I think all in all, it makes for a very good benchmark approach when people want to propose a new method or propose new variables to put in their model. Right? It makes for a very good benchmark approach because it's pretty simple. It's pretty minimal. And this whole special issue for the forecasting competition is under review at International Interactions, and I'm hoping we'll be out in early 2022, but we move way too slow. Okay, so I went a little bit long, but I don't know, Carl, do you want to take a break? I'll just take questions. How about I just take questions? We don't take a break.
Yes, I think I have tons of questions. If you do not mind, I think now we have let's have the audience take precedence, and Ismarai Gonzalez, then followed by Tanyi. Ismarai, please go ahead.
I'll stop sharing my screen so I can answer directly and actually see people. But if I have to go back, I'll just pop it. Okay, Ishmarai. Hey.
And hi, Professor. So I had a question with regards to your measurement in which you compared Nigeria and Libya, how it did better in Nigeria than in Libya. My question was what are some basic factors that are hindering the models from doing better in one state than another?
Yeah, it's a really good question, and that's what I have to explore a lot more. I have some ideas. I think the violence in Nigeria tends to be more concentrated geographically. Like there are some regions that are pretty consistently see some violence, mostly in that northeastern region of Nigeria, in the Lake Chad region where Boko Haram operates. There's pretty consistent violence over there. And when there's consistent violence, this type of model is going to do a good job getting it. Now, Libya, I think it's more disaggregate. And I don't think the violence is quite as concentrated. And so I think it misses a lot more. And so, there's different ways that maybe you can so you have to think about different ways then to accommodate that and account for those differences to do better in places like Libya. I think that's what it has to do with, though. I think it's about the concentration of violence.
Thank you, Professor.
Okay.
And then, my apologies. I had a follow-up. I had another question, but I can wait for something.
No, go
Go
ahead.
ahead, please. Go ahead.
My apologies. So my other question was, so these grids that you mentioned, how are they measured? Are they measured, is there a specific measurement, or is it like region-based, or how does that work?
No, it's totally agnostic. So it's just like the entire world was just basically gridded out, right? And they're like, what are they, like 50 kilometers by 50 kilometers or something like that. And that's it. So there's no, it doesn't take into account any political anything or any geographic anything, right? It's just kind of lines on a map.
Okay, thank you.
All right, Ken Yi, please go ahead.
Thank you, Dr. Ho. Well, Professor Durazo, it's a great presentation. Thank you for that. I'm thinking about the replication of the study. Well, I'm in, like I said, I'm a PA, public administration major. So I feel like this approach, well, you call it benchmark approach, I think is a framework that could be used for another scenario. For instance, the anti-racism protest or movement, or in the US, or it could be used for, say, the corruption issue, like the sexual harassment or scandal in China. Say, this just more context can be. I mean, it can be applied to different contexts, not only limited to the conflict or violence in the Africa region, right?
Yeah. So it can absolutely generalize. The thing to keep in mind, so for protests and different types of protests, absolutely, because these are events. And so the idea of this, this type of approach is very good when we are forecasting like social and political events. If we're talking about, you mentioned like corruption.
Right, like a scandal or
maybe it might do okay there. It's not quite. I'd have to think about what that data actually looks like, and if that is like event level data in the way that conflict and protest are event level data. But so this type of modeling is absolutely, though, portable to protests. A lot of the same people that do the conflict forecasting modeling also do models of different types of social protest.
Do you worry about the overfitting?
Because violence and protest often are associated with one another.
Sure. Thank you. Oh, I was asking, would you worry about the overfitting problem for those
in which
context?
In like protest or moving to a different type of event?
Right.
Yeah, absolutely. You're always going to worry about overfitting. And I mean, when you're doing predictive modeling, overfitting is like one of the main concerns. But it's especially a concern when you have really, really flexible machine learning algorithms, which we increasingly do. These autoML algorithms, you know, with like ensemble learning, I mean, they search over really, really large solution spaces. And so overfitting is a concern, always a concern.
Thank you so much for your
All
answer.
right,
Appreciate it.
let me, yeah, thank you. Glenn, after Glenn's question, maybe pass on to the Taiwan side. Any questions from the Taiwan side? Glenn, please go ahead.
Yes, hi. Wonderful presentation. Thank you very much. It was very interesting work. But one of the things that strikes me, and I look at understand, you know, looking at the intervention on the predicted versus the actual violence and evaluating the intervention. But I wonder about predicting violence that is not begetting violence. In other words, the model seems to say, hey, where there's violence, we're going to see more violence. And that's okay, I get that. But what about areas that aren't having violence, predicting them becoming violent?
Yeah.
Kind of for those not indoctrinated to Hollywood, kind of like Tom Cruise's Minority Report, right?
Oh, excellent reference.
I
have a story associated with that exact movie from my undergrad class very recently. I would love to tell you more about it. So the question is about in places where we don't see violence, and how the model is going to do. So it's not gonna get it unless it's unless there's like violence in the neighborhood, right? But what it will pick up on, what you would hope it picks up on, is if there's a little bit of violence detected, because remember, this is grid month level data. And so if there's violence that is detected 1 month, right, the hope is that it will pick up on that and we'll be able to forecast either increases or decreases in the next month, right, or next string of months, based on, you know, how this grid and this type of violence has appeared in the past. And so the hope is that the model is going to pick up on it very quickly. But the fact is, you know, think about the conflicts a lot of the conflict in Africa, right? A lot of these things go on for many, many, many months and cover regions that expand, you know, that include many different grids. So the kind of the cold onset isn't something that happens too often. Most of the violence that we see in the world had preceding violence. The vast majority of it had preceding violence. Right? If you're measuring it at the monthly level, I mean, every month after a conflict began has had preceding violence.
Mm-hmm.
And so the idea is we're trying to get all of that. And but the approach is going to miss those like cold onsets. Hopefully it picks up on it.
Yeah.
Thank you.
Oh, Peter, do you have any questions from your side?
Yeah, but yeah, the question has been asked pretty closely because the question here was the predictive model relies on the previous distribution of the violences. And so highly disaggregated data is one of the major issues. So the question was, how does model or how you detect a situation like, you know, escalating tension between states, yet no previous conflict or has been a long time, like over 5 decades, has not happened.
Yeah.
You know what I'm referring to, you know, because here we're in Taiwan and the cross-strait situation is quite, you know, in a high tension these years. So I think the background of the question comes from there.
Yeah. So So this model isn't gonna get it. It's just not gonna get it because it doesn't have the features to do it. Now, where some people have had success in this type of thing is by analyzing the text of news reports. And so by analyzing the text of news, you can get at those tensions. All right, and the idea is that, well, you can read the news today in the same way we read the news and say, hey, there's increasing tensions, there's an increasing likelihood of violence. You hope that the model is going to pick up on that, assuming you can incorporate, detect tensions well in the news. And some papers have done a really good job, some forecasting models. I'm thinking there's a 2018 paper by Muller and Rowe who had an entry into this competition in the APSR. They have a very good example of incorporating text into conflict forecasting models. And then there are a couple papers by Thomas Chatterfu who does forecasts violence entirely using text of news reports. And actually the model does quite well. And he also had it. He also had entries into this competition. So people are using text on the Brandt et al. Paper. We used event data, and so this is text that then was processed and events were extracted and used as inputs into the model, and that did pretty well too. And so people are using text from news reports to kind of either forecast entirely at this low level or like supplement models at this low level. And that's one direction. Like if I were to add more variables to the DV-only approach, it would be something based on news reports. So hopefully get at those increasing or even decreasing tensions.
Okay.
I have a question myself, Vito. I think you mentioned a DV-only model, and it's actually you're actually saying this is parsimonious and actually is really powerful just by the dependent variable itself. So would it be because you have some highly temporally and spatially dependent dependency in these variables, then that means this method will be particularly good at this kind of data, this highly contingent temporally and spatially, and also more. These kind of variables are more resistant to interventions like any policy, unless there's a really strong policy that is making things change overnight or at a large extent. So this kind of data will be still, because of the high dependency, particularly good for your model. And this is one question. The other question is, can you explain a bit more about the three autoML systems? And I checked the CMU system versus the MIU system. That discrepancies are high, and particularly for the CM models, and the MIU see such a high fluctuation over a matter of like 4 or 5 months. But your H2O model system is predicting quite low in MSC. And I don't know, the third question is whether you also try out other AOC or BOC, AIC or BIC, they're particularly good for model comparisons. Would they give you very consistent results too? Yeah. Sorry, I have so many questions because I'm particularly interested in your way of handling this, and it must be a very strong teamwork, and it's one person work, it's a lot of work in this project. Yeah.
So
Okay.
yeah, thanks, Carl. So I'm gonna answer them backwards. So the H2O system, at least for these versions of the algorithm of the AutoML engines, which are over a year old, the ones that we used, was much more consistent throughout.
Mhm.
And I think that's due more towards issues with the NYU and CMU systems at the time. I don't think it's I don't think it's like a broader AutoML thing, but I think rather, the NYU and CMU systems were coming at the end of a long DARPA project, where DARPA would continuously throw new things at us, seemingly random, and so they were always like adjusting to handle those new things, and we kind of then threw a brand new problem at the systems to see how they would do. So I would expect, though, AutoML systems on the whole to perform a lot more consistently, like H2O. We don't see major fluctuations. Like, for example, here we see some major movement in NYU, and it's kind of hard to explain what's going on there. I mean, it might just be that it timed out, it got hung up, it had to return a solution that was not the best solution. There was a bug, lots of things like that. But the H2O is much more consistent, at least in this version. Now, all of these have newer versions out. You can find CMU and NYU at datadrivendiscovery.org.
Yeah, I saw that the D3M website. Yeah.
Yeah, the D3M website, Data-Driven Discovery.
The two Ravens are there.
Two Ravens is up there, yeah.
Yeah.
Front-end system. That was our contribution to that project. But it didn't make it into this presentation, though. So.
Right in the middle. Yeah. Anyway.
So the other question about the dependencies, or really just a comment about the dependencies. I mean, that's a feature here, right? That's one of the things that I mentioned early on. Is that we know this about conflict. Like, we know there are very strong dependencies in conflict and violence, and so we want to have an approach that's going to account for that. And I really think that the combination of the flexible AutoML algorithm with the many different ways of representing violence and past violence does a really good job at capturing like the dynamics of a conflict. And so actually in the paper version of this, I actually call the DV only model the dynamics model, because I see it as capturing. I see it as really capturing the dynamics of a conflict.
Yes.
The dynamics of violence. And it's really just focusing on the dynamics of violence and not anything else. So.
Yeah.
Yeah.
Yeah. And do we have more questions? Otherwise, I would come up with more questions, technical questions for this speaker. And while I'm waiting, maybe I have one more. And so I'm thinking, and how you can extend this. I'm still thinking there are certain variables are particularly apt for this and very good for this kind of forecasting. So you have now for some policy people, for sure, they want something more on the right hand side. They always think, oh, this right hand side would do better, will help and predicting. Now I understand all this about different algorithms. Will there be some variables or some problems will be better for intervention? So better for the right hand side instead of just predicting itself. And I'm thinking now violence is contagious, and some for example, even COVID will be highly contagious too. And I'm thinking about something we can do intervention policy to make things alleviated with some strong intervention, strong policy. So so can you name some examples that we can improve? I think it's still about the variables you're predicting, and maybe some certain variables we can more improve using the intervention or policy.
Yeah, I mean, the thing is, like, if you want to estimate causal effects, then you have to build your model to estimate causal effects, you know, and like, and a lot of that has to do with manipulating or you know, establishing your research design. And I saw this a lot on the D3M program, where a lot of times, you know, people were interested in using these predictive models to get like, okay, well, what's the effect of this intervention going to be? I said, well, but that's not what the model's for.
Yeah.
That's just not what it's for. I mean, we have models for that type of thing. You know, we have research designs to estimate causal effects, and we have predictive models to do other things. And if you want to, you know, have a data-driven expectation about what the violence is going to look like in the next month, 6 months, year for a grid, country, region, and predictive models will help you do that. And if you want to assess, I think it will also help you to assess the impact of policy interventions, because you can, with predictive modeling, you can get very good expectations about what violence would have looked like, counterfactual, you know, in the absence of an intervention. So it can help you there. But if you want to know what the causal effect of something is going to be before you do it, you have to really adopt a different approach from the start.
Yeah. I think I'll reserve the opportunity for questions to other audience. And May, you have additional questions? Then Tianyi, May, please.
Okay, well, thank you. I certainly don't know nothing about violent events, so this is a good lesson for me. But I think that your model has two major advantages, and based on what I heard from you say, is first that violent event lasts for 2 to 3 months, and then you try to predict 6 months out. And therefore, your validation stages and use 2 to 6 months data and fine tune the model to do a good prediction in the 6 months out. And the other thing is that the temporal and spatial lag, I think that make a good case of the persistency of the events distribution 6 months out. But you didn't say that how much is the lag you are looking for. It's like the time lags for every month or 3 months or 6 months, and how big is your spatial lag? That's one question. And if I may, I can ask second question, is that in GIS, when we do the space-time analysis of events, we have I'd say common approach is first we will do exploratory analysis. So imagine we have a space-time cube. So it's like a grid expanded in spatial grid, also stacked up to the temporal vertical dimension. So it's space-time cube. Then we were looking at the density of events in each cube over space and time to identify like a persistent hotspot, emerging hotspot, or diminishing hotspot over space and time. So if your model can do such a good prediction of violent events, and I imagine that those events are very persistent in space and time. In other words, that if we look at the hotspot analysis, we see those events are not moving much over space, but pretty much persist, robust over time. Do you think that's maybe the case?
Yeah. So on the second point, yeah, I think that's think that's probably the case. I think it's the case that this model's doing, it's doing a very good job getting conflict where conflict is like a hotspot, like you said, where it's persistent over time and space. And so like, you know, think of the Nigeria example I put up at the end. Like we're doing a good job in Nigeria. The violence there is pretty persistent, you know, month after month, and in particular regions. And so, you know, we do a reasonably good job forecasting. It would be interesting to see, you know, to do that type of like exploratory, like space-time or hotspot analysis, to identify those hotspots and see if like, hey, these are in fact the places where the model is doing well.
Mm-hmm.
So, I mean, is there, yeah, so I guess the question would be how to do that.
Oh, if you give me an event, I can look at the preliminary result and see how it does. So that should not be too much trouble. But I think what is the very smart of your part is really the validation stage of your machine learning, and that you use that time frame to fine tune your model for the period of prediction you try to look outward. So I think that's the smartest move of your model creation.
Thanks. Thanks. to answer the first part about the size of the legs. So legs that are in there are only one grid over, and it's you know, it just has to be touching the
so
grid.
you look at the immediate neighbor.
Yeah, just the immediate neighbors for the spatial legs.
Uh-huh.
And the time legs go back up to 12 months.
Mm-hmm.
But not everything goes back up to 12 months. Most of it is just looking at violence at time t-1.
Mm-hmm.
But then some things are looking at measures of violence back to, you know, up to 12 months, up to a month in the past.
So in your AutoML, you actually look at multiple leg and then find the ones that give you in the validation stage, give you the best prediction.
No, they're baked in, but what we should do eventually is exactly that. Set those up as tuning parameters and see what works best. But right now they're just baked in.
I see.
Mm-hmm.
Well, still pretty good. Congratulations.
All right, and Tian, you have one more question?
Just a quick question, Dr. Ho. Dr. Derazio, I have to be honest with you. I don't get the machine learning part, but hopefully, you know, in my future, you know, PhD journey at UT Dallas, I can take your class or Dr. Ho's class to get that. But just hypothetically speaking, I'm more curious about the time dimension when you have create models to evaluate or to modeling the conflict event. Does the time does the event happen more recent, has more weight, or they're just like equally weight? Like I came up with this question because I'm a student, also I'm an investor. Or in the marketing field, when we do the analysis or giving insight to client, we typically give the most recent event more heavier weight compared with the event happened more like 2 years ago, 5 years ago. It maybe have some little impact, but you know what I'm saying. So how do you handle this in your model?
So the algorithm estimates the weight, right? We put the legs in there, and then the algorithm will give weight to the different legs. But looking at the results and looking at the variable importance features, the ones that are weighted the most are the ones from the previous month. They're the one month legs. And in particular, it's the lag of the dependent variable, which is the log level of violence. And the most important one is the count of the number of fatalities. excuse me, the count of the number of fatal events. And those are both for the previous month. And it's within that grid. So it's actually the spatial lags don't do quite as well as I thought they would. Most of the predicted capacity comes from like 1 month, different variations of measures of violence in a 1 month lag within the unit.
Oh, I can imagine the algorithm is really powerful. Thank you. I appreciate it.
Okay, thanks for the question.
Hello. Do we have any more questions on the Taiwan side, Peter? I don't want to take too much, of time.
All right. Here's a couple of questions related. I think one of them is kind of touched upon by Kenny. It's about the generalization of the models. Think about generalization. What counts for social or political events? So it's pretty. We relies on data heavily. So the events don't count. That's how we think about it here.
Yeah.
Okay, and this is one question. The other one is related too. And can you talk about a little bit more about the geographical events data? Does it covers like which area of the world, which region of the world? Can you?
The GED data covers everything.
Uh-huh.
The GED data covers everything.
Mm-hmm.
So they have event data. That covers everything. Right. Another good event level data project. It doesn't quite cover everything, though. What covers a lot of the world is armed conflict location and event data set, ACLED, ACLED. That's another one.
Yeah, great. Yeah.
Very good event level data. ACLED has data on protests. GED, if I'm not mistaken, doesn't have data on protests, but ACLED does. So, yeah. So the coverage is broad with GED. It's global, and it integrates very easily with the PRIO data. So if you're interested in conflict data, PRIO, the Peace Research Institute in Oslo, is one place to go for some really good conflict data. And in particular, the data that they put together for the Views project, I mentioned this in my talk, is up on GitHub. They can even give you instructions to get access to the data. Really, there's a lot in there. I mean, it's pretty impressive. So to the first question, so what counts as events, or where I think this approach could generalize? It's kind of contextual, it's a little bit subjective what counts as an event or not, right? But events all share certain core attributes. There's actors involved. There's a particular type of action that we think is, social or political, has social or political relevance. There's a actor's action, and there's a specific date and specific time. And so we're not talking about something that happened in a 6-month period, or we're talking about things that, have a specific date and time. Usually happen, you can give a city or a, latitude and longitude, and give the coordinates of the event and happened at a particular time. And so, I think of different types of violent events. So conflict-based events, state-based violence, which is what we looked at here, one-sided violence, which would be Boko Haram attacking or bombing a village or something like that. That would be one-sided violence. Different types of protests, different types of repression. incidents involving crime or police or other security forces. Those tend to be the events that we see. I'm trying to think of what other ones we see like this modeling used for.
All right. Yeah.
So broadly social political events, but exactly what that encompasses can be, it's kind of subjective.
Mhm. All right, and do we have more follow-up questions, Peter?
Not for now.
Not for now. I
Yep.
think I'm reading 10:57 now. It's getting a little late, and maybe we can wrap up. And I really want to say thank you to Vito and also all the guests coming in and different time zone. I understand, and I think this is just begging for more teaching or more. You should be waiting for next talk by Dr. Vito DiRezio. I think there must be some more questions. I have a lot more questions I want to learn directly from him. And back for the next event, probably in either UT Dallas or in Taichung, Taiwan. And hopefully that will happen soon. This is something we're working on. And quickly, I wanted to invite you, use this couple of minutes to invite you. We have more talks upcoming in the lineup. And next week, we will have Dr. Jimin Lee from University of Texas at Austin. And he will talk about a talk titled The P-Value Controversy. This is really interesting and give you a new idea how to interpret models now and whether we use UTP value. Another one is the one after that is Professor Ji Yong Jiang, and I call him Johnny. He's one of the most prolific psychometricians, and his talk will be about social network analysis in the framework of SCM. If you're taking the SCM course or you're interested in linear models, SCM models, and social network analysis models, he will talk about the latest innovations, and he received an NSF grant to have a lab on that. And please stay tuned and join us in the upcoming DAC events. Yeah, I think I'll wrap up. I want to thank Dr. DiRezio again. And Peter, do you have any concluding remarks?
Yeah, just wanted to say thank you, and thank you for staying up so late, especially for those from the United States. And thank you. Stay tuned, and I hope to see you soon next time. Thank you very much. Thank you, Vito.
All right, let's get a round of applause. Thank you,
buddy.
Thank you, Vito. Thank you very much. Yeah.
All right, thank you.
Good night, everyone.
All right. Thank
Good
you.
night,
Good
bye.
night. And yep.
Good night, Dr. Ho, Dr. Pan.
Thank you.
night.
Thank you, Tianyi. I'll see you tomorrow. Yeah.
See you tomorrow.
Yeah. All right. And I want to thank you for those who are in Taiwan and Taichung, and thank you for your attendance. And look forward to seeing you next week too. And next week, and Dr. Lee will give a very good talk too.
Okay. Thanks, Dr. Ho.